So if we're looking at this like we were the last problem, if we kind of peek ahead, we can see that if we just, when we take the derivative, we're going to get a dr dt, a dx dt, and a dy dt. So that already tells me, because I was only given 2 of those 3 things, or information about 2 of those 3 things, that I'm going to have to do another replacement, all right? So for this one, when we take our derivative, right, we're going to get 2r dr dt equals 2x dx dt plus 2y, dy dt. And I already see that my 2's cancel, but in order to solve this for dy dt, I need to know what x and dy or dx dt are. So x and y I have. They were given, that was the point given at the beginning of the problem, the 3, 7, root 5, right? R I can find by plugging it back into this equation, so that's not too bad. So we can actually find, because we're going to need an R as well, right? But then to get dx dt, I have to use the fact that I had a second relationship here. So I'm going to take the derivative of this guy. So on the left, I get dy dt. On the right, I get 7 times 1/2 2x minus 1 to the negative 1/2 times 2 dx dt. That's just a chain rule. The 2's cancel, and I'm just going to clean this up just a bit to make it easier for me to work with. So this is actually 7 over the square root of 2x minus 1 dx dt. So now I can solve this for dx dt, and I get the square root of 2x minus 1 over 7 dy dt equals dx dt. So it's just like the cone problem where we had to solve for the dr dt to get the dh dt to plug it back in. It's just a substitution. So I can go back up here to my derivative. I also need to find r. So r squared, right, is x squared, which is 9, plus y squared, which is 49 times 5, because when you square 7 root 5, the 7 squared is 49, this is 5. So r is the square root of this. So this is the equation, that I want to substitute everything into. So my r is the square root of 9 plus 49 times 5. dr dt is negative 2. X is 3. dx dt is the square root of 2 times 3, which is 6, minus 1. So I get the square root of 5 over 7, plus y, which was 7 root 5 dy dt is what I'm solving for. So then I just subtract that negative 2 up front. I subtract a 3 root 5 over 7 from both sides. And then I divide everything by 7 root 5. So this guy we were talking about in class, it's really, really ugly to look at. But it was more about getting the process down of if you have two variables and we're missing some of the information, right, we have to use the second relationship to solve and substitute. So those are about as bad as related rate problems get. When you've got two variables in the equation and you're missing one, we have to give you that second relationship to just go substitute back in. This one, there may have been a way to rearrange it and put it in at the beginning, but I don't think it would have been very pretty. It was going to be ugly either way, because I think I worked it out both ways when we were editing the problem, and there was really no, you know, the first problem, it really made a lot of sense to plug in that R at the beginning and get everything in terms of H.
Wait, how did you get 9 and 49 again?
49 and 5 again?
Yeah.
That 9? Okay. So right here, when I needed to find R, right, I plugged my X and my Y and my point into here and solved for R. So R squared was, X squared was 3, so 3 squared is 9, and 7 root 5, 7 squared is 49, square root of 5 squared is 5. Yeah. Yeah. So I would definitely recommend web work, practicing some more of these problems just to get the process down. But it's draw a picture, label all your variables, find the model, take dt, and then from there on out, it's really just algebra. Do you have all the pieces you need, and can you plug it in right? Yeah.
The problem that I'm having is like trying to set up the problem. Like when we're given stuff, and I don't know like, okay, this is this is that, and this is the formula I'm going to use to solve for what I need to solve for.
So you have trouble getting to the formula, or just like putting everything you were given together?
Yeah, basically like putting everything like I'm given together. Like I understand, like I can identify like if I'm solving for like dr dt or like dh dt, but it's a matter of like, okay, what am I using? Like what's my formula that I'm going to take the derivative of to solve for
Okay.
that?
So one thing that helps me is even before I can label the variables, so like if we go back to this guy, so even before I even can assign the proper names to the numbers, right, I really have to sketch a picture of what it told me was happening. So once I sketched the picture, I know what this pillar of salt looks like. I knew it was a cone. I could draw that. Then once I saw the cone, I was like, oh, cones are height and radius. Those are the dimensions. So some of this, you've got to know a little bit of geometry for these types of problems. Because if I saw a sphere, I would know, oh, I want to measure this in terms of R. And then I start looking at the units. So even sometimes before I write the volume, I saw that this was 3 inches cubed, and I was like, oh, that's the unit of volume. And I knew we were adding salt, so it was positive. And because it was, sorry, this should have been inches per second, I think. But now that I see that's a rate, well, that's volume over time. So I want the volume of a cone. And then that set me up to write this formula. So it wasn't just an all-in-one. I knew from the beginning of the problem, there really was a logical chain of events that took me there. So drawing the picture, like the dough problem where we had the cylinder, I drew a cylinder and then I could see, oh, cylinders have length and radius, right? So you do have to be familiar with the geometric formulas for the shapes. That will help you assign variables. Then when you go back and reread the question, the numbers should sort of make a lot more sense of what they're describing. So if it's something in inches cubed, that's just volume. But if it's inches cubed per second, that's the rate of volume. So that helps me. Then once I've got the model, then from there, it's just taking the derivative and plugging things in. You know, I'm pretty okay once I get there. But you can't always just read the problem, especially in this one. So in this one, it was a little more nuanced. Right? This one was a little trickier because it said, well, you're going to take points on this curve and you're then going to find their distance to the origin. So I just started with the distance formula. I knew I was allowed to square it to make the derivative easier, right? And then I said, all right, well, I'll plug in a 0 into these 2 points, right? Because one of my coordinate points was fixed. and that reduced it down to the Pythagorean theorem. So this wasn't obvious for everyone to jump straight to the Pythagorean theorem. And so that really, when you do the web work, that's gonna what's like, I would go in and do some practice problems and practice setting it up. Do you know what the scenario is? Do you know what the shape is? I mean, that you only just get from just doing a lot of these. You just have to practice, yeah. Anything else?